Okay, remember work, and this is section 14.1. Work is a force applied through a distance. So in order for a force to do work on an object, it's got to move that object through a distance. The unit, well, since it is work is a force, which is a newton, through a distance, which would be a meter, the unit is a newton meter, which is also called a joule. Okay, a joule of work is a newton meter. And remember, you can have positive work. Positive work, what would that mean? The direction of the force, how does it compare to the direction of movement?
Force and motion are in the same direction.
Yeah. So if you have positive work, good. Positive work means that the force and the motion are in the same direction. And I'm writing all this stuff down because I've been asked to record this lesson today. And the only way I have to record it right now is Smart Recorder, and it only records what's written on the board and my voice. So, eventually I'm going to have a camera set up, and I'll start recording classes with the camera so you can see demos and stuff also. Anyway, what about negative work? Yeah, it's not that hard, y'all. Not that hard. Negative work means, right, for not just different direction, but force is, yeah, let's put it that way. Force direction is opposite. Motion. Okay, so can somebody give an example of positive work? Anything? Applied, so let's call that applied force, right? Pushing something or pulling something. We usually call that applied force. Anything else you can think of? I can think of one. You could look up. What kind of force did you just do on it? Let go of it. What kind of work was done on it? Gravity. So was it positive or negative work? Huh?
Positive.
Positive. Why is it positive work?
He's pulling down, object's pulling down.
That's the kicker. Was the movement in the same direction as the force? Yes. Positive work was done. Y'all get it? Okay. Can you think of an example of negative work? If the heat's running, you're going to shout it out. Can't hear. Do you think you got your hand up, or you just chill it? Trying to think of it. Lane, you got one? No. You almost got one? In that case, yeah, and now y'all got to look at the situations. Mason, You are absolutely right. I'm not gonna write it on the board. Well, I'll draw a picture here in a second, how's that? But lift your book up again. Okay, in the act of lifting up your book, here's book, right? When you lifted it up, what all forces were acting on it? Gravity in what direction? What else? Yeah, applied force in what direction? Up. Okay, so let's look at it this way. Applied, and the motion was up, right? Okay, so in that case, applied force did what type of work? Positive. Positive work. What kind of work did gravity do? Negative work. Because it was opposite the direction of motion. Okay? Now, yes, sir. Friction. So easy. It ought to just pop in your head immediately. Push your book across the table. Okay? Direction is this way, right? Direction of motion is that way. What all forces are acting on the book? Okay. All right. So we got gravity in what direction? What else? In what direction? Let me calibrate that thing. Okay, what else? What direction? What else? Look at your diagram right now. The way you have it written right now, that book should be going down through the table to the center of the earth. We call that normal force. It's a support force. We call it normal because in physics, normal means perpendicular. It's perpendicular to the surface. Physics having a whole lot of fun with that right now. Okay. So, we can assign work to every one of these forces. So let's examine. Normal force, is it doing work? Remember, only forces that are parallel to the direction of motion do work. If the forces are perpendicular to the motion, no work is done. So what do we assign here? Work equals 0. What about on gravity? Work equals 0. Okay, applied force. Positive work. Friction. Negative work. Okay? And all of that work is in what unit? Joules. Joules. You can look at the photographs, the figures, and that helps you to review this concept on the board. Pages 412 through 413. Okay. The math is really easy on this stuff. Work equals force times distance. So, if a weightlifter lifts a 1,600 Newton dumbbell, a height of, let's call that a positive force. The distance is a positive 2 meters. How much work is done? Okay. Why did I write the plus there on those two values?
So you're at
So that tells you what? What kind of work? Positive work. Okay, so what do we do here? Work is what times what?
force times.
Yeah, force times distance, so what is it? Okay, how'd you get that? Okay, so what is it? That's it. That's how you do that. It'll get a little bit more complex if you decide to come back and take physics senior year, but not much more. Work is really easy. Power. Y'all done with this? Who said no? You better speed it up and quit goofing off back there. I'm not blind. I see what y'all are doing. I'm waiting for my moment to move you. You're not going to hold this class back. Power, capital P. Power is the work done on an object in an amount of time. Now, work is force applied through a distance. So for a specific task, when we talked about with cutting grass, for a specific task, there's a set amount of work that has to be done. The difference is not work, it's time. Remember? It's time. Like the example we had was, which would you rather cut the yard with? You know, cut the grass with? A pair of scissors or a riding lawnmower? Well, choice is easy, right? Riding lawnmower. Same amount of force has to be applied through a distance. The difference is time. It's going to take a whole lot less time to use the riding lawnmower than it is to use a pair of scissors to cut that same yard, right? So please understand that. So power is work divided by time. The unit, well, look at it. Work is measured in what? Joules. Time is measured in seconds. So a joule per second is a watt. And that W means watt. That's the SI unit for power. But there's also horsepower, which is HP. And remember, there was a conversion. If you guys look at page 416, 1 horsepower is 746 watts. If I ask you to do a conversion, I will give you that conversion. I will not ask you to memorize it. But remember, I think we tried to figure out how many, what was it, 60 watt light bulbs would be the same amount as power as a car engine or something like that. They both are measuring power, it's just in different units. As a matter of fact, I don't know, but I would be willing to bet that in Europe, you would see like units like megawatts instead of horsepower. I don't know that for a fact, but I know they do that with everything else on the car. Like, if you look at your car tire, pressure is listed in both pounds per square inch, PSI, which is an English unit that America uses, but it's also listed in kilopascals, which is what Europe and the rest of the world use. So I would be willing to bet they would do the same thing with engines. Okay. One more thing I want to mention about work before we leave it. Whenever we describe work, with respect to the system, not surroundings. Here's what I mean by that. Hold your book up in the air, please. Getting the work out this morning. It was good for you. Then you do this piece of cake. Okay, right now, is any work being done on the book? No. The book is the system. The system is the one object that we are taking into consideration. Right now, no work is being done on the book. Then how come you're feeling it? Okay, yeah. Also, work is being done on your muscles. But in this particular situation, I did not ask about your muscles. I asked about the book. So the book would be the system. Your muscles would be the surroundings. Do you see what I mean? Anytime in physics that we talk about work, we are talking specifically about the system. What work is being done on the system, on the object in question. You put your book down here. Okay, so that's 14.1. Chapter 15. Let's flip over to chapter 15. Hmm. 446. Okay, what is energy? Oh. So why are we putting work and energy in the same unit? They're related. So now we can redefine work. In section 14.1, we defined work as a force applied to a distance, and that's still true. But we can expand on that, and we can call work a transfer of energy. Flip your book. Come on, you can just let me quit already. How did your book get from there to there?
Energy, work.
Okay, so does your book have more, less, or the same potential energy? More. How did it get more potential energy?
Time.
You transferred energy from your muscle to the book. Okay. Kinetic energy. It's energy of what? So that means KE is 1/2 mass, because it depends on the mass, times the square velocity. That's the motion. Okay, we calculated those. We did the practice set. Not hard to calculate, just watch square your velocity. Okay, what is potential energy?
Energy of position or combination.
Okay, we looked at two types of potential energy. We looked at gravitational potential energy, that's what the subscript G means, gravity. Okay, what does gravitational potential energy have to do with? All energy has to do with mass, but gravitational potential energy also is dependent on
Gravity pulling down. And
the force of gravity, the acceleration due to gravity, and the what?
height.
Height. Where m is mass, g is acceleration due to gravity. Anybody remember what that value is? Good, 9.81 meters per second squared. And what is h? Height. And height needs to be in meters. Height needs to be in meters. Okay, the other type of energy, where we did not calculate it, if you take physics, you'll calculate it then. Elastic. Elastic potential energy. Okay, where gravitational potential energy is the potential energy, bless you, associated with height from Earth. What is the elastic potential energy? Yeah, stretching a rubber band, pushing a jack in box in its box, stretching out a slinky, spring, elasticity. Yes, Leah. So this is potential energy associated with stretch or compression. Of some elastic object, something that can retain its shape, its original shape, is something that has elasticity. Can it achieve its original shape? So springs, rubber bands, stuff like that. All of this energy is measured in what unit? All energy unit is what? Nope. Energy is the ability to do work, not power. Joule. Yeah. SI unit for energy is joules. A joule is a Newton meter. A Newton is a kilogram times meter per second squared. Okay. 450. Not do this as a bonus. Unit manipulation. Unit manipulation sounds kind of weird, so physicists call it dimensional analysis. There's a fancy word for you. Okay. What is a Newton equal to? F equals ma. What? Remember Newton's second law, F equals ma. What does Newton measure?
Force.
Okay, force. Force. So yeah, Newton's measure force. Okay, force is mass times acceleration. So what is the unit for mass? Kilogram. And F equals m times a. What is the unit for acceleration? So if you forget it, that's a way that you can remember what the definition of a Newton is. It's a kilogram times meter per second squared. Right? Okay. Joule is a Newton meter, right? And what did we say a Newton was? Kilogram, so I can replace this with this if I need to. And it's times a meter, so that would be what? A kilogram times meters squared per. Okay. And what is the unit for power? Watt. Okay. And what is the equation for power? Work over time. Good, Beth. Work over time. So a watt, what is the unit for work? Joule. And the unit for time? Seconds. So then I could go in and plug this in there. You see how you can just keep manipulating units? You know, we can go further. What's a joule?
Kilogram.
Yeah, you could plug in that. You could plug in Newton meter. You could plug in this, right? Kilogram times meter squared, second squared over a second. So what would that make it? Kilogram times meter
Square.
over seconds
Cube.
cubed. See, it just keeps going on and on and on. So let's go back to some old stuff. Velocity. What is velocity? Okay, velocity is distance over time. And what do we measure velocity in? Meters. Distance over time, get it? Okay, and what is acceleration? Change in velocity over time. And what is velocity measured in? Meter per second, time is in second, so that becomes what? Meters. Okay. So, you know, I may put some sort of bonus on there where I'm asking you to plug in units and see what they come out to be, like I just did here. That would be bonus. If you are up for it, try it. If you don't want to mess with it, you don't have to. The only reason I'm doing that is because that is something that is counted in grades in senior physics. Not optional for senior physics. So I want you to start getting used to it. Okay. Types of energy. Okay. Mechanical energy. Mechanical energy is simply the sum of kinetic energy plus potential energy, all forms of potential energy of an object. So that jack in the box, the system would be the spring, right? So we could look, remember you always have to have a reference point, but we could get its kinetic energy. You know, if it's shoved in the box, what is its kinetic energy? Nothing, zero. We could get its gravitational potential energy by its height relative to the Earth. We have to set a reference point. And we could get its elastic potential energy. You add all those up together, you got mechanical energy. I will not give you specific examples. This stuff here, guys, from this point on is all definition. Okay? All these other forms of energy I'm about to give you, you will learn in senior physics that they are called non-mechanical energy. Non-mechanical energy. Thermal. What is thermal? Yeah, it's heat. Okay, and we have chemical. Yeah. I'm just putting ditto marks for energy. Okay, so chemical energy is, and it's a potential energy. It's a potential energy stored in chemical bonds. when we eat food, our body breaks these chemical bonds, the energy is released for us to do, to work out, to walk across the room, to breathe, for our heart to pump. To move our mouths, whatever. Electrical energy. If you will flip over to 452, page 452, that's some pretty lightning. I like that. Scan through that paragraph. What is the most important point? Electrical energy is associated with what? Electrical charges. So, if you were to say that electrical energy was lightning, well, yeah, but that's not the only kind of electrical energy. What are some other, what's some other examples of electrical energy? Will's looking at it. How are we getting these lights right now?
Electricity.
Well, how's that work? Electrical charges, electrons are flowing through a copper wire. That's how we're getting that. So that is electrical energy. Okay, we have electromagnetic. Okay, when you take chemistry, you will learn a lot about this. This is what type? It's energy that travels through space as what? In other words, it's light. That's what we call it. It's light. Light is an electric wave and a magnetic wave moving through space at right angles to each other, but you'll learn that when you take chemistry. Okay. Page 454. Oh, my bad. I skipped that one, didn't I? Thank you,
Nuclear.
Grant. Nuclear is what? Nuclear energy is energy of the nucleus. It's the energy stored in the nucleus of an atom. And there's a whole lot of it in the nucleus. Thank you. Will you hold that up so if I can see it, Leah? Thank you. What's happening? Okay, so can we get more specific? Okay, so me turning this handle, this crank, what kind of energy is that? Mechanical, good, mechanical energy, and now we have electrical energy, and then we have, not chemical, we have thermal, and we have electromagnetic, light. So what's happening right now? Energy conversion. So energy can be converted or changed into different forms. Mechanical is being converted to electrical as the electrons flow through the wire, and then electrical energy is converted into electromagnetic, that's the light we see, and thermal, the heat that's built up. Right? The more energy I put into it, put a little bit of energy, What's happening, Leah?
It's barely
It's, the filament is barely
flow.
flowing. Right? Y'all get it? Okay. Okay, so energy can be converted from one form to another. Energy is conserved. What does that mean? Yeah, you need to know the law of conservation of energy. Which says what? Energy cannot be good. Energy of the universe is constant. AP Chemistry just learned that that is the second law of or the first law of thermodynamics. We're going to stop there. We will not do section 15.3 because we're out of time. Bell's about to ring. So I recommend that you do this. Go through these notes, watch this video. It's Professor A.E. Jr. is the YouTube channel. What?
You send that online?
Yeah, sure.
I can find it.
Okay, yeah, I will. And go back through these pictures in the sections, sample problems for the math, section reviews, section assessment questions to test yourself, definitions. But do not look at the definitions for section 3 because we're out of time. Have a good rest of your day.